I feel like it articulated in a really nice way the criticality of water for all living things. We talk about our planet being the blue planet and how important water is for the sustaining power for all living things. We know water is a really unique compound, and it's used in tons of chemical reactions, has a lot of unique properties that make life available. For scientists who study space and look at other planets all around our solar system and universe, the key thing they're always looking for is, well, is there any water on this planet? It's hard for us to imagine that life could exist without water. So of course it has a lot to play with human economy and human access, and because our species relies on water in all kinds of complex ways. In addition to the life thing, the infrastructure thing is a big element, but also ecosystems. So we're going to talk a little bit about water today, and we're really going to use, I'm trying to find my mouse, a springboard from the geologic history piece and the climate and weather piece. So here are our learning objectives for today. There are only 4. They're really discrete. I put them in here the same order they appear in the textbook. You may have noticed that this reading was assigned before the last assessment, and it's because there was some relevance about water resources for weathering and erosion. It was hard to understand all of that without thinking about some of the processes around water and the movement of water. But now we're going to talk about it really explicitly, so there'll be a couple key things. We're going to do it in the reverse order, though, because I want to start with the connections to the water and what we've already talked about, and then we're going to get into the key terminology and talk about sources of water and movement of groundwater. This graphic is fantastic. If you look at this graphic, there are 3 bars, and each bar going from left to the right is looking at what is the breakdown of water and where it's found compared to the bar that's on the left. So although water, the blue planet, we have tons of water on this planet, not very much of that water is available for living systems. Most of the water is salt water, oceans, about 96%. Only 2.5% is about fresh water. If we take that 2.5 and expand it out, the places where we find that fresh water is not always readily available. So some of it's underground, some of it, of course, is in lakes, rivers, and streams. Some of it's bound up in ice, and some of it is on the surface where we can find it. Of the water that's on the surface, some of that is frozen, and some of that is sequestered in places like swamps, and a very small proportion of it is the part that's available. So this kind of graph is really nice because it just sweeps and it shows you what all these relative proportions are. Let's do a little bit of some computational analysis, and I think about 3 minutes is appropriate for these 4 questions. We've got 3 math questions to digest and understand this table, so practice this, and then the last one is a little conceptual piece. Calculator is probably necessary. If you can do this in your head, you're a stud. seconds here. All right, so what do we got for the last one? Let's take it from the bottom. Which of these 5 sources are available for human purposes, do you think? There's actually a very heavy interest, because of the limited amount of water, to take from other quantities. What do we think? Andrew?
Surface water.
So surface water for sure. And what do we think of this entire 122,000 number? Is all of that available? Do we have to do anything with any of it before we can use it?
Yeah.
What do we have to do, you think?
In terms of drinking.
Okay, clean it up if we're going to drink it. What else do we use water for? For some other purposes. The amount that we drink is a very, very small, minute number. Sometimes we have to transport it, so it's available, but it's not where the people are. We have to move it. That's a big thing. That's been one of the key drivers to why civilizations are where they are. It's a major historical link. What else? What else do we use water for? Growing plants, just for the yard, or
Growing food.
for food production. It's huge. It's fabulous. All right. What other surfaces do we think are available? Anything else, or this is the only one?
Groundwater.
Maybe groundwater. Do we have to do anything with that to get it? Ready?
Yeah.
We got to transport. We always have to transport that. Not many cities underground. None, in fact. What else? Any of these other sources? Atmosphere, oceans, glaciers, anything?
Glaciers, potentially.
Anything we'd have to do with glaciers to get it ready? Melt the ice. Really the only one that's the best is the surface water for sure. So when we think about all of these sources, it's a very small percentage. I like this graph, by the way, because it shows you there's about 12 million total cubic kilometers of water that's salty, that's in the ground. And then there's a whole bunch that's in different types of lakes and surface lakes, another 85,000. Those are saltwater lakes. We'll talk about that more in a second. So what is the percent of water that's fresh for number 1? What do we get here? It's about 2.5, which you could have grabbed from the last graph, but it's also an easy math. It's this over this, 1 over 2. But the total fresh water, how much is frozen?
69.5.
It's a huge amount. Over 2/3 of it is frozen, essentially unavailable. And then how much of the water is on the surface? So if we all agree that the surface water is the most readily available source of water, you can see it's a 0.3%. It's a very small number. And if we restricted access to any of that through pollution, or if it's in an area where we can't use, that number is even smaller. Excellent. Excellent. Let's keep going. So the availability of water is not uniformly distributed. So when we say, well, it's in the surface water, but it's not in a place where humans can use, or we have to transport it, where water is on this planet is fairly predictable. But it's also variable across the entire planet. This shows a couple months of data, and it'll just play on loop. I really like this. So we got evaporation, which is the water going up into the air. What do you notice about that top graph? Why is it strobing like that? What's the association? Why does it get this kind of blinking effect? It's the sun. And what about the sun?
It's day-night.
Day-night. Day-night. So the energy from the sun that we've talked about, it has the potential to lift water molecules into the air. That's where this all starts. Then it becomes water vapor, and you get all of this swirling. Why all the swirling and moving around? Where do you notice most of the water vapor is, by the way? Latitude and longitude-wise. We had to spatially characterize it. It's at the equator where there's a lot of energy, right? And there's also a lot of water there. Fabulous. What else? In precipitation, what do you notice here? What kind of patterns do you see? Where is there a lot of precipitation? Equator. And where is there almost none? Things we already know about. Where's there almost none? None at the poles, pretty much. Where else? There's a couple other bands where there's not a lot happening. Right here, right? 30 degrees north and south. So the availability of water is not uniform, and the availability of water through climate and weather forces. But what we see, and so here's going to be a new layer onto this, is that the proximity of land masses to water also has a role to play. So large bodies of water impact the climate, and these are the specific ways. And so whatever is the predisposition of that area for climate and weather, it exacerbates and stabilizes that state. So the availability of water usually stabilizes. That's the thing I want you to get out of this. So warm oceans evaporate a lot of water, and then there's a lot of precipitation. So places like the equator, or places like 60 degrees north and south. And cold oceans evaporate a lot less. And so those areas, they condense, and they're usually drier. But no matter what the state is, it usually has a stabilizing effect. You've probably heard this, I don't know why. Adults love saying this sort of thing, especially when the weather changes, as you would expect, like right now in October as we move from one season to the next. Well, you don't like the Missouri weather, just wait a minute and it'll change. What the variability of climate and weather in continental interiors is much higher than it is at places close to bodies of water for these reasons. Excellent. We're going to use specifically the terminology in this class, the hydrologic cycle. I like the Greek roots, but I also want to make sure that we're tying this cycle to the other biogeochemical cycles that we'll explore later on during this portion of our class. Sorry about the text is a little bit small on this slide. But the big idea is that this is powered by the sun. And so all the things that we've studied about climate and weather, they come up here. And the places where the sun's energy is the most intense, this is where we have the fastest acting changes. So here's a couple key terms, and we already know them, so I'm going to go pretty quickly. But evaporation refers to the amount of water that's not gas. It's not water in its gas form. It's water molecules, small water molecules that are just lifted into the air by air molecules that have a lot of kinetic energy because of thermal energy, right? And so evaporation is that movement. We're taking water from whatever it looked like and we're carrying it into the air. When it starts to clump together and form larger particles, we call that process condensation. Of course, precipitation is when there's not enough energy for the air to hold them anymore, and they start to come back towards the earth. And then this is the next key piece that we haven't talked about very much. So this is the one new key term, infiltration. So when the water percolates or infiltrates into the soil, we're moving the water from the atmosphere into the lithosphere, and we call the movement of water in that process infiltration. Infiltration. So we're going to layer together a couple things here. Here is our first case study. As part of today's lecture, we'll do 2 mini case studies, and we're going to look at the 2 most important water phenomena in North America. So the water cycle, the hydrologic cycle, is powering this surface water is particularly key. We're going to watch this video twice because it's pretty short. There's no narration, there's some annoying music, but I want you to try to get through these 3 parts. So describe the movement of water. So if I ask for a description in this class, it's usually associated with a process. It has a beginning point and it has an end point. And in the middle stages when things are happening, that's where I need you to add the most flesh. So as you watch this and you think about this description, 3 to 4 sentence answer is perfect for full credit on something like this. So the movement of water across this watershed. The second one, discuss the formation. So how is this watershed formed? They're going to give you a few key elements, but think about the geologic history of this area. You have some background knowledge. And then, how large is it? The last one, describe the impact of the Mississippi watershed. What does it have on the American economy? Ready to go? Again or no? Again? Again, all right. Practice answering these. 4 minutes is about what you would get for this set of questions on a case study like this. So let's talk about this. Let's talk about this a little bit. Let's take the middle one first. So the formation of this, how do we think it was formed? Some information that we maybe know from the past. How does it come together? So glaciers is one big thing. The glacial history of North America, something that we've talked about a little bit. So if you look all the way to the left, because we're in North America, we should have some resident knowledge about this. What is the boundary that's all the way here on the left as you look at it? What do you think is right here? So we have the Missouri River, and the Arkansas River, and those both started here. What's this? The Rocky Mountains. And then what's on the right? The Appalachian Mountains. So you can see this huge bowl has been carved out by movement of water over millions of years and movement of ice sheets from the last ice age, the Laurentide ice sheet. So we've seen some things. What is the size of it? And give me some of the data, because the data I think is impressive. What's some of the relevant data to help us articulate the size of it? Yeah.
So 1.24 million square miles.
1.24 million square miles. It's a huge area. Okay, what else? How does that put it in context of some other ones? Go ahead.
The watershed covers 31 states.
31 states. Tens of thousands of tributaries and streams that flow into it. What else? Oh, really?
Yeah. Oh, it's also 2 Canadian provinces.
This is 2 Canadian provinces as well. What else?
4th largest watershed in the world.
4th largest watershed in the world. The Amazon rainforest is the biggest. We've seen some things about the Amazon. It's number 4 compared to that. All right, what else? Any other pieces of relevant data? Let's get into the data for number 3. How key is it? What do we use it for? What stakeholders care about this? Agriculture.
Consumers.
Consumers. How much do we care about it? How important is it for these stakeholders? They gave you some data as well. Extremely. Like 92% of crop production comes from the availability. In the same way that crops are using that area, ecosystems too, right? Very key. What about the first one? If we had to just describe the movement, now that we have this whole thing, which way does it go? How do you describe it to somebody if they're just looking at this picture with no movement?
Flows to the south.
Flows to the south. And that's it.
It empties into the Gulf of Mexico.
Empties into the Gulf of Mexico. That's a key point.
Starts Lake Itaska.
In Canada. Starts at a lake in Canada. What were you going to say, Kyle?
Well, I guess if we're saying the entire watershed, I guess it flows inward to the Mississippi River. So
Beautiful. So some of the major tributaries flow inward from the Rocky Mountains and Appalachia. That's great. And do those flow north to south? They flow towards it, right? Mostly, if they're on the Rocky Mountain side, from west to east, and if they're on the Appalachian side, from east to west. And they all go towards it. Good. That kind of language, this is something I've noticed is hard for our class, and we need to improve that skill. So how do we describe the way something looks? So we need to be using those types of observations, and then how do we articulate it to somebody who has never seen it or doesn't know about it? Good job. Let's keep going here. Let's keep going. So that's a little bit about rivers and streams and the watershed, because that area blankets a huge space. That's where most of the water is available. So rivers and streams are probably the most critical form, at least for human purposes, of water availability. But we also have some aquatic systems on the land as well. And ponds are always small, but lakes can vary quite a bit in size. So this graphic over here on the far right, I like this graphic. I know it's a little bit hard to see, but each one of these is a different lake on our planet. This is the Caspian Sea, for example, and then we have some of the Great Lakes, Huron, Superior, etc. So if we look at this top bar, this shows the volume. So how big is the Caspian Sea? It's huge, right? Not a trick question. But if you look at this next one, how deep is it? It's kind of in the middle. So how much space does it cover if it has a ton of water and it's not very deep?
A lot of space.
A lot of space, right? Likewise, if you have a lake that's extremely deep, it could have a huge volume of water. But those ecosystems and the way that water looks and the availability of that water looks a lot different depending on its composition. So most of this is runoff. And so we have weathering and erosion, but we also have leftover parent material and leftover sediment from when saltwater oceans receded, like what we have in North America. And so it affects the composition of the lakes. Lakes vary a lot in salinity. So for example, the Great Salt Lake in Utah, that has a lot of resident salt left over in it. and so it's a very salty lake. On that first graph, that would have been in the 85,000 cubic kilometers. That's not very, it's not very ecosystem friendly because of that salt water. But we also see that salinity also is increased because of runoff and weathering and erosion. Some of these lakes are formed not through glaciers, but through resident glaciation and tectonic activity related to the geologic history of the planet. So every lake has a story to tell, but there's usually only 5 or 6 different stories. It's either tectonics or ocean receding or previous runoff. And the main thing that they all, it's water that basically just stays there. Sometimes there's a little bit of in and out, but most of the water going in is from precipitation and runoff, and then out is some small tributaries. So they kind of remain in their space for a long period of time. Excuse me. We just discussed weathering and erosion a little bit. So here's a graphic. This is from the textbook, and I like this graphic. So it shows kind of a before and after. So if I look at this, which one of these 3 types of soil is probably the most weathered? It's experienced the most erosion. The what one?
Clay.
Clay, right? And how do I know?
There's the smallest part.
And what's the association between small particles and weathering and erosion?
It takes more weather and erosion for particles to get smaller. That's why you see, like, especially in younger soil, you'll see big chunks of rock compared to older soil where you will see more sand, silt, and clay.
So that weathering and erosion, that's exactly right, is what breaks down the parent material into smaller particles. So the smaller the particles, and these are the smallest. Now look at the infiltration rates for each of these 3 types of pure soil types. Sand, which is really large and porous, allows for a lot of water to flow very quickly, and clay doesn't allow for water to move very quickly at all. So soils, they vary in texture and parent material, and the weathering and erosion has a lot to do with the rates of infiltration. There is some chemical traits as well. So whatever, because water is a polar molecule, the chemical traits or the chemical properties of the parent material also has a role to play at how much repulsion forces and the flow of water. We won't get into that very much here, but just to acknowledge that it is a factor and it is a thing. And we can also alter the chemical composition, and I just wanted to throw this out here because it'll come up later in the class, so it's kind of like an honorary mention at this point, but you're not accountable for this. But if we add acidity to the soil, it changes the composition of the soil, and particularly that chemical piece as well. So whatever is the chemical composition really affects the rate of the flow of infiltration, the rate of infiltration through soils. So we've talked about surface water, rivers, tributaries, and streams. We've also talked about lakes and ponds. Now let's talk a little bit about groundwater. The word that you should associate the synonym with groundwater is this word aquifer, and perhaps you've heard of that before, but this is the anatomy of what an aquifer looks like. This is a very general picture here. What you'll notice is when water is underground, you sometimes hear, well, it's like a giant lake, which is true, but it's also not true. It's not like a giant cavern with an underground lake that's just underground. It's water and soil all mixed up together. And so this is what it kind of looks like. So you have an unsaturated zone. This is where the water is infiltrating through the soil. The saturated zone is where it starts to pool up. And you'll notice both of those zones are filled with sand, silt, and clay. It's in the ground. So if we need to get this water out, like we talked about on the first slide, used for human purposes, we have to filter it through sand and move it, and it's not perfectly easy. It's not as readily accessible as some of the other forms. So the saturated zone is where it's all at. One thing that you'll notice, this level right here is called the water table, and that's the highest level. And if there's an adjacent body of surface water, the highest level elevation of where that lake or pond is usually about even with what it is for the groundwater. So we see this phenomenon a lot. I put in this picture that shows the way soil looks under a microscope. So when we mix it up, we tried to separate it so we could actually see. We're going to deal with our soil samples on Thursday here. But this is big sand clays, and the space in between is called the pores. And this is silt, these little ones, and then the clay is right here. So you can see the clay particles are like 10,000 times smaller than the sand particles. So the more clay, the more dense. But if we have this is where the water is going to flow through. So the water flows through the pores, and when it gets saturated, it just fills the pores, right? And so all of this is what we refer to as an aquifer. And the movement of water goes in through this process called recharge. So the rate of recharge is equivalent to the rate of infiltration. And then withdrawal is wherever the water is coming out. So we're moving that. And the water table is where the level is between saturated and unsaturated. So if we ever take more water out than the water is going back in, then the water table is going to go down. Does it make sense? It's an obvious thing. If we zoom out a little bit, we can see that there are actually kind of two different categories of aquifer. We have a confined aquifer and an unconfined. The unconfined looks a lot like what we just talked about. So you can see the water table level is about even with an adjacent body of water. This is where the water is being infiltrated through. So any of the water that falls on this surface of land that infiltrates through these soil types is going to go into this aquifer. There can usually be a space of rock that's not permeable, so this could be hard bedrock. But you could have an aquifer underneath that, or you could just have a confined aquifer without an unconfined one on top of it. And that means that this is only recharged from a single point. It's not recharged by water flowing through the soil, because there's some barrier or something that isolates the ability for the water to infiltrate through the soil and access that aquifer. So a confined, those is where water is being pushed in and out through infiltration. And unconfined, those need to be pumped out. So you can see, for human purposes, this is a little bit about the access piece. And then the recharge areas have to be carefully managed so that the water table doesn't recede to a level where it's no longer functioning. This slide, it's kind of a review, but I just wanted to show there's a couple different images from the text that I think are cool. They're useful. So this area refers to, this is before heavy pumping, and then if we're taking more water out than we're recharging, well then the water table is going to go down, and it's going to go down at the fastest rate by where the well is. Likewise, if we get salt water coming in, there's usually some rock barrier between the water table and the saltwater intrusion. And so if we penetrate where the water table goes down below that, then the well will be contaminated with salt water and will no longer be useful. So there's a lot of risk with the amount of water that we use from aquifers. Which leads me to our last case study for today. So there are, again, two North American phenomena that are really critical. We already looked at the Mississippi watershed. Now we're going to look at this thing called the Ogallala Aquifer, and I'd like you to do a few more things with this. So we've got 5 tasks. One is identifying stakeholders, and they only give you a few explicit, so I need you to stretch a little bit. I'm increasing the demands slowly over time with this. Talking about soil composition and how it relates to the aquifer. Talking about the relationship between the Nebraska sand dunes, which is a recharge area, and water resources in North America, and then looking at the impact a little bit. One is on the North American economy, and then one is how is usage of this aquifer related to water resources for the rest of the continent. Where did I put my mouse? Here it is. All right, we're ready? Here we go.
When summer these rows of corn alone seem to go on forever. In 2013, farmers here planted 100 million acres of this one crop, the largest amount since 1933. But there is a place in Nebraska where the farm fields come to an end. A place where there's nothing to see but dunes of sand. It's an area known as the Nebraska Sandhills. Here, rolling dunes cover 20,000 square miles of land, making this the largest formation of dunes in the Western Hemisphere. The Sandhills were created during the last ice age, when this region of North America was suffering from severe drought. As winds blew across the dry earth, great dunes of sand were formed. Later, thick grass and plants took root, stabilizing the sand and creating this remarkable landscape. But these dunes play a key role in making Nebraska an agricultural powerhouse. They're part of a complex ecosystem that is responsible for supplying Nebraska farmers and millions of people across the Great Plains with the precious water they need to survive. That's because under the Sandhills is a geological formation that contains vast amounts of water. It's so big, it stretches under the states of South Dakota, Wyoming, Nebraska, Colorado, Kansas, Oklahoma, Texas, and even New Mexico. It's like a giant underground lake and is called the Ogallala Aquifer. The impact of this aquifer on the American economy is astounding. 30% of all groundwater used for irrigating crops in the U.S. comes from this one water source. Scientists discovered the Ogallala Aquifer in the 1890s, but even though they knew it was there, farmers didn't have an effective way to get that water out of the ground and onto their crops, which is one reason they suffered hard during a famous period known as the Dust Bowl. In the 1930s, farmers across western Nebraska and throughout the Great Plains were overplowing their fields after years of good rain and productive yields. When the rain stopped, the winds started to howl, picking up giant clouds of dust, since the grass to hold it in place had been plowed under. It destroyed entire fields, blinded cattle, and ruined machinery, bringing farmers to their knees. One farmer later described what happened. The birds fluttered, the rabbits ran, and the sky turned black. We thought it was a twister. The dust lay so thick in the back bedroom we just moved the mattress into the middle so we could sleep. Many Nebraskan farmers lost their farms to clouds of dust, even though those same farms stood right on top of one of the greatest sources of fresh water in the world. At the time, the technology to tap that water successfully had not yet been invented, which is why the Great Plains was often called the Great American Desert.
All right, there's a
Mexico.
brilliant link to our history and society in the small group of people around you. Try to work through these 5 questions in the remaining time. I do want to talk about one thing here that came up a lot on the exam, and you'll see when you